standing on a dust particle. Somewhere between the core of an atom and the edge of the observable universe, we exist. Not especially large, nor especially powerful. A species capable of great intelligence and great confusion. This is a story about size and about how incredibly, mind-bendingly small we really are. We'll begin here with you. Humans scale the illusion of being big. We walk upright, we stretch our arms, we build towers. It's easy to feel large, but the truth is, we only look big to ourselves. A human is roughly 1.7 meters tall. The world around us, our rooms, streets, cars, is built to fit that scale. Our perception of normal is rooted in that. But compare it to a blue whale, 30 meters, Mount Everest, 8,848 meters, Earth's circumference, 40,075 kilometers, even on our own planet. We are specks. The microscale, the invisible empire. Dive inward. A red blood cell is about 7 micrometers wide, just 7/10 of a meter wide. A strand of DNA, just 2 nanometers across. And the atoms that make up your body, they're mostly empty space. If a hydrogen atom were the size of a football stadium, its nucleus would be a grain of rice at the center. Everything else is nothing. Zoom in further. Proteins fold themselves into complex machines only a few nanometers wide. Viruses are 20 to 300 nanometers. Ribosomes, your body's protein factories, are 20 nm. The electron cloud that surrounds an atom, a probabilistic blur. Go smaller. Proton radius, 84 femtometers. Planck length, 1.6 x 1035 meters, the smallest possible unit of space, as far as we know. It's not just that we are small. We are made of things so small, they defy intuition. Your body is a galaxy of particles obeying quantum laws that we still barely understand. The human body as a cosmic city. Your body contains 37 trillion cells, 10x more microbial cells, 100,000 kilometers of blood vessels. Every cell is a bustling metropolis. DNA strands uncoil and replicate. Proteins are assembled. Mitochondria power the entire thing like tiny generators. Ribosomes function like automated factories. Neurons pass signals as fast as 120 meters per second. Zooming into the brain. You have roughly 86 billion neurons. Each makes thousands of connections called synapses. Total synapses, 100 trillion. As many as stars in a galaxy. Inside you, systems more complex than cities are operating silently. And they all run on molecules smaller than the wavelength of light. From trees to planet sizes that make us blink. Now zoom out. Consider scale on Earth. A redwood tree, up to 115 meters. Boeing 747 to 70 meters. Burj Khalifa, 828 meters. Cities from above resemble microchips. Cars look like cells. Roads like blood vessels. Planet Earth. Diameter, 12,742 km. Surface area, 510 million km. Mass, 5.971020 GG. Population, 8 billion tiny humans. From space, Earth is a pale blue dot. Clouds swirl. Lights flicker. But life is invisible at this range. Planets, stars, and the impossible scale of the solar system. Our sun is massive. Diameter, 1.4 million kilometers. Volume? can fit 1.3 million Earths. Mass: 333,000 times Earth's surface temperature. 500 C, but it's just one of over 100 billion stars. Distances in the solar system. Moon: 384,400 km. Mars: 225 million km. Jupiter: 778 million km. Pluto: 59 billion km. Voyager 1, launched in 1977, is now over 23 billion kilometers away. Still moving, still sending, and yet it hasn't even left the solar system's influence entirely. The galaxy isn't even trying to be comforting. The Milky Way, 100,000 light-years across, contains between 100 and 400 billion stars. Our Sun is 25,000 light-years from the galactic center. We orbit the galaxy once every 230 million years. It's shaped like a disk, but with arms like a spinning pinwheel. Every dot in the night sky is part of it, but most of it we'll never see with the naked eye. We live in a spiral arm, a quiet suburb of an ancient city of stars. Cosmic web, a universe made of islands. Galaxies cluster together. The local group, 50 galaxies, Virgo cluster. Thousands of galaxies, Laniakea supercluster. Over 100,000 galaxies. These clusters are strung together into filaments. Between them, voids hundreds of millions of light-years across. The structure resembles neurons. The universe itself has a kind of cosmic brain, with galaxies for nodes. The observable edge. The observable universe is a sphere. Radius: 46.5 billion light-years. Diameter: 93 billion light-years. That's how far light has traveled since the Big Bang. We don't know what's beyond it. Maybe it loops. Maybe it doesn't. We can only see what light has had time to reach us. So even with our best telescopes, most of the universe is still hidden. Fractals and the pattern of existence. Nature copies herself. Trees branch like lungs, rivers meander like veins, galaxies spiral like storms. From Romanesco broccoli to hurricane patterns to neuron structure repeats. The universe is built on self-similarity. Maybe this is more than coincidence. Maybe the math of nature is universal. We are patterns of smaller patterns. Nested systems. Self-aware fractals. You, again in perspective. So where does that leave you? You are 70% water, made of atoms forged in stars, living on a tiny rock orbiting a mediocre star. And yet, you can think, you can imagine the size of a galaxy, you can measure it, question it, wonder at it. You are small, but aware, and in this cosmic vastness, that may be the rarest thing of all. What if the messages we send into space are a mistake? The question nobody wants to ask. What if humanity made a mistake so huge, so dangerous, that we haven't realized it yet? A mistake that has been traveling through the darkness of space for decades. A mistake we cannot take back. A message that might already be on its way to someone or something we do not understand. We've been told that sending our voice into the universe is beautiful, a symbol of hope, a sign that we are not alone. But what if the universe is quiet for a reason? And what if breaking that silence was the worst thing we could have done? Let's find out. The first messages humanity sent. We began with good intentions. A golden record attached to Voyager, a plaque on Pioneer, a binary beam launched from the Arecibo telescope. Images of humans, mathematics, our position in the galaxy, our chemistry, our voice, our music. We imagined someone gentle finding them, someone curious, someone like us. But space is not a fairy tale, and innocence is not a shield. Our messages are still traveling outward, and we have no control over where they go, or who will decode them. The warnings we ignored. Stephen Hawking once said, "If aliens visit us, the outcome could be like when Columbus landed in America, which didn't turn out well for the natives." But we didn't listen. We told the universe where we live. We sent our address in mathematical form. We broadcasted our biology, our DNA structure, even our bodies. We assumed advanced civilizations were peaceful. But look at Earth. The more advanced a species becomes, the more dangerous it can be. So here's the uncomfortable question. What if the first civilization that hears us is not friendly? What if aliens don't think like us? Humans assume logic is universal, but what if alien logic is nothing like ours? What if our peaceful message looks threatening to them? What if our symbols mean something violent? What if our math is wrong in their eyes? Imagine an alien mind trying to interpret our signals with no shared culture, no shared biology, no shared reality. Our drawings, our numbers, our music, our chemistry, our voice could be seen as a warning, a claim, or even a declaration. Not peace, but territory. Not curiosity, but challenge. Not friendship, but danger. And the scariest part? We won't know how they understood our message until it's too late. The paradox of silence. For decades, scientists wondered, why is the universe so quiet? Maybe because every civilization that shouted was found and erased. Maybe silence is not emptiness. Maybe silence is fear. A universe full of worlds that learn to hide. We are the only ones, speaking loudly into the dark, and the dark never answers. At least not yet. Should we stop sending messages? Right now, scientists are divided. SETI says, listen, don't talk. METI says, talk, don't fear. Who is right? If we stay silent, we remain invisible, safe, hidden. If we keep broadcasting, we may attract something that sees our message as an opportunity or a target. The debate is no longer scientific. It is existential. Do we risk everything for the possibility of connection? Or do we stay quiet and survive? The message is already out there. But here's the twist. Even if we stop today, it's already too late. Our first TV broadcasts, our first radio waves, our signals of wars, of speeches, of music, of chaos, have been traveling through space for almost 100 years. Earth has been shouting without knowing it, and those signals could already be reaching other civilizations. Right now. What we should send instead. If we want to be heard safely, we need messages that cannot be misread. Mathematics, constants, physics, patterns of nature. Not culture, not politics, not biology. A whisper, not a scream. A greeting, not an invitation. A signal that says, we exist, we are curious, we are cautious. The final question. And now the question that bothers every scientist. What if someone has already answered? What if a signal is traveling back to us, right now, hidden in the darkness, crossing the void, getting closer every year? Maybe the silence isn't silence. Maybe the answer is on its way. And when it arrives, we will finally learn whether sending our first message was a sign of brilliance or the beginning of our biggest mistake.
Sunsets are an amazing phenomenon that we are used to seeing on Earth. They vary in shades from golden, orange to purple, becoming a mesmerizing sight thanks to our atmosphere. But what do sunsets look like on other planets in the solar system? Where the atmosphere is made up of other gases and the laws of physics behave differently, we can observe something completely different. Let's dive into this unusual journey and find out more. Mars, a cold blue sunset. On Mars, sunsets are quite different from those on Earth. The red planet is known for its thin atmosphere, made up mostly of carbon dioxide, and its dust storms give everything on the surface a reddish hue. However, sunsets on Mars are colored a cool bluish color. This is because dust particles in the Martian atmosphere scatter blue light more efficiently than red light. Imagine the sun setting on the horizon, and everything around you is colored in shades of cool blue. It's a sight that is both mesmerizing and creates a sense of loneliness in this desolate world. Jupiter, swirls of red and brown. Jupiter is a gas giant, and it has no solid surface from which to view the sunset. But if you were at the level of its clouds, you would see something amazing. Jupiter's atmosphere is rich in hydrogen, helium, ammonia, and other compounds that create its famous stripes. Sunset on Jupiter is a succession of vivid red, brown, and golden hues mixed with an intense swirl of clouds. In the distance, flashes of lightning and storms complete the picture, turning the sunset into a true cosmic show. Saturn, golden and creamy hues. Saturn, with its rings, is often associated with splendor. Its sunsets are also marvelous. Saturn's atmosphere is made up mostly of hydrogen and helium, and when the sun sets behind clouds, the light diffuses to create soft golden cream hues. It's a sight that seems incredibly tranquil compared to stormy Jupiter. Imagine the shadows of Saturn's rings laying over the planet, adding even more magic to this picture. Venus, a hellish orange-yellow palette. Venus is known for its dense atmosphere made up of carbon dioxide and clouds of sulfuric acid. This makes sunsets on Venus quite unique. The thick atmosphere of scattered light creates an orange-yellow palette, but at the same time, visibility is extremely limited. Sunset on Venus resembles the dawn of hell. The light is bright, almost aggressive. The atmosphere of Venus is so dense that the light is distorted, creating a hazy glow. Titan, a fabulous combination of blue and orange. Titan, a satellite of Saturn, stands out among all celestial bodies with its thick nitrogen fog. Sunset on Titan seems like a fairy tale. The sky here takes on a bluish hue, smoothly changing to orange and pink due to the presence of organic molecules in the atmosphere. Imagine Saturn's ring shining through against this soft glow. This place is perhaps one of the most mysterious places to watch sunsets. Uranus and Neptune, ice blue sunsets. On Uranus and Neptune, the atmospheres contain a lot of methane, which absorbs red light and reflects blue light. Sunsets here are cold, almost icy, and colored in deep blue and turquoise hues. However, because of the vast distance from the sun, the light seems dim and the sunsets are long, slowly slipping away over the horizon. It's a veritable dance of light and shadows at the edge of the solar system. What happens on exoplanets? Now that we've explored sunsets within the solar system, let's look beyond it for a moment. Scientists have discovered thousands of exoplanets, worlds orbiting other stars. On these planets, sunsets can be quite unusual. For example, on planets with 2 or 3 suns, you can see several sunsets, one after the other. Imagine a sky that is encompassed by 3 stars at once, each coloring the horizon in its own unique hue. On an exoplanet like WASP-1b, where the atmosphere is incredibly hot, sunsets can be bright yellow or even green due to rare chemical elements. And on water worlds like those depicted in science fiction, sunsets can reflect off the ocean surface, creating a kaleidoscopic effect. Each sunset is unique, and its beauty depends on the atmosphere, gas composition, and distance from the star. They remind us how amazing and diverse our cosmos is. As we gaze at a sunset on Earth, we can imagine what wonders lurk on other planets and satellites. And who knows, maybe one day we will be able to not only imagine, but see these incredible sunsets with our own eyes. If you enjoyed our space journey to the sunsets of other planets, don't forget to subscribe to the channel. More amazing and informative stories about our world and beyond await you here. Give us a like, share the video with your friends, and be sure to press the bell so you don't miss new episodes. Your interest is our motivation.
When it comes to the most mysterious objects in the universe, the first thing that comes to mind are black holes, monsters that devour everything in their path. They bend space and time, turning light into an invisible prisoner. But what if there is the exact opposite of these monsters, something that does not consume, but erupts matter? White holes are one of the strangest and least understood concepts in astrophysics. According to Einstein's equations, if black holes exist, then white holes must also exist. But why can't we see them? What is a white hole and how is it different from a black hole? Why does its existence challenge our picture of the universe? Could a white hole be a portal to another reality or even the other side of a black hole? This topic raises so many questions that if they are true, we'll have to rewrite the whole cosmology. What is a white hole? In 1916, Karl Schwarzschild, studying Einstein's equations, derived a solution for the space-time curvature around a massive object. It described two possible solutions. A black hole ordinary an object with such strong gravity that nothing can escape beyond its event horizon. A white hole an object from which nothing can get in, but is only ejected outward. If a black hole works like a cosmic trap, a white hole works like an eruption. Simple analogy. A black hole is the drain hole in the bathroom where the water goes in. The white hole is the faucet where water pours out with no way to flow back in, but this is where the problem comes in. We can see black holes, for example. Their shadow is captured by the Event Horizon telescope, but white holes are not. Why? Why can't white holes be seen? There are several theories to explain this paradox. 1. White holes are unstable. If black holes form when a star collapses, then the reverse process, the explosion of a white hole, is impossible. Any particle, even light, cannot enter a white hole. But how then is matter formed inside it? Two white holes exist, but they're hard to see. They can live very short lives, for example. They can appear and disappear instantly, emitting huge streams of energy. We may have seen such phenomena before, but interpreted them as powerful gamma-ray bursts. 3. They may be hidden inside black holes. If white holes are connected to black holes, they may exist in another space or dimension, ejecting matter there. This leads us to the craziest question ever. What if black holes are entrances and white holes are exits to another part of the universe? White holes as portals to other worlds. One of the most fascinating aspects of white holes is their connection to wormholes. A wormhole, or Einstein-Rosen bridge, is a hypothetical tunnel connecting two different points in space-time. If a white hole is an exit and a black hole is an entrance, then they could work as a portal. What does this mean? Perhaps matter trapped in a black hole does not disappear forever, but is ejected to another part of the universe through the white hole. This could explain the sudden bursts of energy in some parts of space. Maybe universes are connected to each other through black and white holes, creating a multidimensional web of spaces. But there's a catch: wormholes are theoretically unstable. They should collapse instantly, or exist only in the presence of exotic matter. White holes and quantum physics. If white holes exist, they must be described not only by general relativity, but also by quantum mechanics. One hypothesis states that white holes are the final stage of black hole evaporation. When a black hole loses mass due to Hawking radiation, it can eventually explode and become a white hole. This may explain rare super-energetic cosmic flares. Other hypotheses. White holes may be related to the information paradox. Perhaps information about absorbed objects is released through the white hole. They may be a source of dark energy affecting the accelerated expansion of the universe. Can white holes be detected? There are several ways to find them. 1. Look for super-energetic emissions, for example, gamma-ray bursts whose origin is still unclear. 2. Look for strange gravitational effects. Perhaps white holes create strange disturbances that can be detected. 3. Looking for inverse. Black hole affects something that behaves in the opposite way. Future telescopes like the James Webb Space Telescope or next-generation gravitational observatories may give us the answer. If white holes exist, the universe is not at all what we thought. White holes could be the key to unraveling the most complex questions in physics. They could confirm the existence of mole holes and the multiverse, explain the disappearance of information in black holes, become a bridge to understanding quantum gravity. Imagine if we ever find a white hole, a portal to distant worlds. And now a question for you. Do you think white holes exist, or is it just pretty math? Write it in the comments. White holes are one of the most mysterious and explosive ideas in modern physics. If they really exist, it would literally revolutionize our view of the universe. Why are white holes so important? They break the usual laws of physics. White holes, in theory, do not absorb, but eject matter. This contradicts the second law of thermodynamics, which says entropy chaos must always increase. They can explain the Big Bang. Some physicists speculate that our Big Bang could have been a white hole from another universe. This means that our universe is just part of an endless chain of birth and destruction. They may be connected to the multiverse. If black holes are connected to white holes, it could mean that they create tunnels between different universes. They could be the key to quantum gravity. There is no theory in modern physics that unites quantum mechanics and gravity. White holes could be the bridge that helps connect these two systems. Why can't we see them? White holes, according to Einstein's equations, should only exist in reverse time. This means that if they were in our universe, we would never be able to see the moment of their creation because they appear as pre-existing objects. But here's something that begs the question. Maybe white holes exist for a very short period of time, eject matter, and immediately disappear. Maybe some quasars and gamma-ray bursts are white holes, but we don't realize it yet, or white holes are hiding behind the event horizon of black holes, and we just don't know how to look for them properly. The future of research. Right now, we have no direct evidence for the existence of white holes, but technologies like gravitational detectors, X-ray telescopes, and quantum computing could bring us closer to the truth in the coming decades. If white holes exist, it will change everything. It would be a real explosion in astrophysics that could lead to a new theory of the universe. My prediction? I think that within the next 20 to 30 years, physicists will find evidence of white holes or their analogs. Perhaps we will realize that they are not just a mathematical abstraction, but a real part of the cosmic structure. What if they don't exist? Even if white holes turn out to be just a theory, studying them is already moving physics forward. After all, in order to prove that something doesn't exist, you need to understand very deeply the very nature of reality. Either way, White holes are a topic that will be on the minds of scientists for a very long time to come. If you liked this video, give it a like, subscribe, and get ready for new discoveries.
In recent decades, scientific progress has allowed us to look deeper into the mysteries of the cosmos, and one of the most fascinating questions that still remains without a definitive answer is the existence of other worlds or a multiverse. The multiverse is the hypothesis that our universe is not the only universe, but that there are infinite other universes, each of which may be different with its own laws of physics, life, and time. Let's dive into this theory, exploring how it came about, the scientific background behind it, and how it may affect our view of reality and ourselves. What is the multiverse? A multiverse is a concept that describes an infinite number of universes, each of which exists independently of the others. These universes may be similar to our own, or they may be completely different, with different physical laws, different life forms, or even a different concept of time and space. Scientists are considering several types of multiverse, from parallel universes that may be virtually identical to our own, to universes with completely different characteristics. How did the theory of the multiverse come about? The multiverse theory emerged at the intersection of quantum physics and cosmology. Many physicists began to study this hypothesis in an attempt to explain those phenomena that do not fit within the standard models. In particular, the theory of the multiverse arose because of the strange properties of quantum mechanics and the so-called inflationary theory, which suggests that the universe expanded at a tremendous rate immediately after the Big Bang. Types of multiverse. To date, there are various ideas about what a multiverse might look like. Let us consider a few of them. Perpetual inflation theory. According to this theory, our universe is just one bubble universe among an infinite number of other bubbles that were formed by constant expansion. Quantum theory. According to Hugh Everett's interpretation, every choice or event creates a new universe. This means that with each choice we make, many parallel worlds are created in which we make different decisions. String theory and extra dimensions. String theory suggests that our three-dimensional world may only be part of a more multi-dimensional reality. It is possible that there are 10 or 11 dimensions, and all of these dimensions may have their own unique universes. Why is the multiverse theory appealing to scientists? The idea of a multiverse helps explain many mysteries. For example, it can explain the so-called fine-tuning of our universe, the fact that its laws are perfect for the existence of life. If there are an infinite number of universes, then at least one of them must have conditions that would allow life to arise. In addition, the multiverse allows us to explain quantum phenomena, such as particle entanglement, the strange effects of quantum superposition, and even the nature of consciousness. If there are multiple universes, many paradoxes and random events become more understandable. Evidence or speculation. One of the main challenges to the multiverse theory is the lack of concrete evidence. Since other universes are beyond our visible realm, and perhaps even beyond our understanding, their existence is extremely difficult to confirm. But some physicists, such as Lee Smolin and Max Tegmark, have proposed theoretical and mathematical models that may point to the existence of a multiverse. What possibilities does the multiverse theory open up? Imagine that somewhere in another universe lives your double, who has made completely different choices in life. Perhaps there is a world where physical laws allow immortality to exist, or worlds where the development of civilizations has gone much further than on Earth. The theory of the multiverse opens up endless possibilities for our ideas about reality. Also, this hypothesis may change our understanding of fate and free will. If every choice we make creates a new universe, then the question of what will happen tomorrow takes on new meaning. Perhaps there is a universe for every possible future. criticism, and doubt. While the multiverse is a fascinating idea, it also causes controversy and skepticism among scientists. Some believe that the theory of the multiverse is not a true scientific hypothesis because it cannot be tested and experimentally proven. Others, on the other hand, believe that one day we will have the tools to study it. What the multiverse means to us. Even if the theory of the multiverse remains a hypothesis, it has profound philosophical implications. It raises questions about our place in the universe, whether we are unique, and what the limits of our reality are. The multiverse forces us to think about our connection to the world and how our choices can have an impact not only on our lives, but perhaps on infinite other realities. The theory of the multiverse is not just a scientific fantasy, but one of the most intriguing areas of modern physics. It expands our understanding of the cosmos and ourselves, raising questions that may change our perceptions of reality. Perhaps we live in a unique universe, or maybe our universe is just one of many others. Either way, exploring the multiverse opens us to an infinite number of possibilities and uncharted roads. Don't forget to subscribe to the channel so you don't miss new interesting episodes. Your support helps us make our content even better. Thank you for watching.
What happens when extreme space objects collide? The moment of impact. Space is not quiet. Not really. It hums. It crackles. It vibrates with violence. And sometimes in the cold dark, it collides, not gently, not slowly, but in bursts of energy so powerful they warp spacetime itself. Black holes, neutron stars, white dwarfs. These are the deadliest, densest objects we know, and when they meet reality bends, this video isn't just about explosions. It's about the laws of physics pushed to their limits. So what happens when the universe crashes into itself? Let's begin. The densest things in existence. First, meet the players. White dwarf stellar corpses, Earth-sized but with the mass of a sun. They're the end state of average stars like ours. Dense, stable, until they're not. Neutron stars even smaller, even heavier. Just 20 kilometers wide, but with more mass than our sun. 1 teaspoon of neutron star matter would weigh billions of tons. They spin, they pulse, they glitch. Black holes, the point of no return. Pure gravity. No surface. No bottom. Some are born from stars. Some sit at the centers of galaxies. All of them are violent by nature. But when they collide, the real story begins. White dwarf plus white dwarf, the silent supernova. 2 white dwarfs locked in a binary orbit will spiral closer over millions of years. Eventually, they merge. If their combined mass exceeds the Chandrasekhar limit about 1.4 times the mass of the Sun, something terrifying happens. They explode. A Type E is supernova, one of the brightest events in the universe. It leaves nothing behind. No neutron star. No black hole. Just pure light and expanding gas. Astronomers love these collisions. They use Type E supernova as standard candles to measure distance. But for the stars involved, it's oblivion. Neutron star plus neutron star, the gold forge. When two neutron stars collide, the universe changes. First, they spiral toward each other, warping space as they go. The dance speeds up. Time distorts. Then impact. The collision produces gravitational waves, literal ripples in the fabric of spacetime, which we can now detect thanks to LIGO and Virgo. But that's not all. These mergers create kilonovae, explosive events that forge heavy elements like gold, platinum, and uranium. That ring you wear, that satellite part, it may have been born in one of these collisions. What's left behind? Sometimes a more massive neutron star, sometimes a black hole, always a scar in the cosmos. Neutron star plus black hole, the silent devouring. This is not a fair fight. A neutron star approaches a black hole. It spirals in. It begins to stretch, torn by gravity. Then it vanishes. No light, no explosion, just gravitational waves and absence. The neutron star is swallowed whole. Depending on the size, it may be ripped apart, first sending out a flash of gamma rays. But usually, it simply disappears. These collisions are rare, hard to detect. But when we find them, they confirm Einstein, challenge models, and remind us of the universe's appetite. Black hole plus black hole when gravity meets itself. Two black holes don't collide like billiard balls. They merge like ghosts, like gravity consuming gravity. No light escapes, but the collision sends out a shockwave of spacetime, a gravitational roar. In 2015, we heard it. For the first time, LIGO detected the merger of two black holes 1.3 billion light-years away. Since then, we've heard dozens more. Each one a cosmic drumbeat. The result? A bigger black hole, a loss of mass turned into energy, and a permanent dent in the universe's memory. The unseen violence of space. All these collisions happen far away. They don't touch us, but they shape us. The gold in your blood, the atoms in your bones, the iron in your blood. They were made in fire, in fusion, in collision, in collapse. The universe isn't calm. It's catastrophic, and in that chaos, life formed. We are the ash of cosmic accidents. Collisions we haven't seen yet. There are collisions we know must happen, but we've never seen them. White dwarf plus neutron star could lead to a rare type of gamma ray burst. Neutron star plus black hole, plus another black hole, a triple merger. Mathematically predicted, never observed. Black hole with a rogue planet. No one knows what it would look like. And then, there are things we haven't even imagined. What happens when two intermediate mass black holes merge? What happens if a black hole eats a quark star, assuming they exist? We don't know. But Webb might see it, or LISA, or something that hasn't even launched yet. The sound of collision. Gravitational waves aren't just abstract ripples. They can be turned into sound when two black holes merge. They emit a chirp, a rising frequency as the orbit tightens, then a sudden cut-off. It's the most massive sound in existence. A death song. And we're just now learning how to listen. The biggest collision still to come. In 4 billion years, the Milky Way will collide with Andromeda to galaxies. Hundreds of billions of stars, massive central black holes. It won't be a fiery crash. Space is too empty, but the black holes will find each other and eventually merge. A final exhale of gravitational energy. Earth might be gone by then, but the echo will ripple across the universe. A reminder that nothing stays still. Collision is creation. We tend to fear collisions, but in space, they're not just endings. They're beginnings. Every crash reshapes the cosmos, builds heavier elements, sparks new stars, seeds planets, forges possibility. You are made of remnants, of things that hit too hard to survive. That's not destruction. That's birth. Peering beyond the curtain. Since the dawn of humanity, the night sky has been our oldest mystery. Ancient civilizations interpreted the cosmos through mythology, seeing gods, monsters, and the fate of empires in the stars. But as science advanced, we began to see the universe for what it truly is, a vast, expanding, and enigmatic realm governed by laws some understood, some still elusive. But what if, despite all our progress, we're still only scratching the surface? What if everything we know, matter, energy, time, and space, is only part of a deeper, more intricate structure of reality? In recent decades, discoveries across cosmology, quantum physics, and astronomy suggest that there may be hidden layers of existence and seen frameworks shaping the visible universe. This is our journey through those possibilities. The hidden structure of the cosmos. At the grandest scales, the universe is not a random scattering of galaxies. Instead, galaxies form massive filaments and walls that stretch for billions of light years, interconnected like threads in a spider web. This is known as the cosmic web, a vast structure that defies the notion of chaos and reveals a deep underlying order. Galaxies are not evenly distributed. They cluster in regions where invisible matter, dark matter, is thought to reside. This hidden structure shapes the universe's form, guiding the movement of galaxies and the formation of galaxy clusters. These filaments of dark matter can't be seen directly, but their presence is detected through gravitational effects. Through gravitational lensing, the bending of light by gravity, we map out these hidden threads, revealing a framework that spans the observable universe. The existence of this vast skeleton suggests that space itself may not be as empty or as simple as it appears. The visible cosmos may be draped upon an invisible scaffold, a hidden layer we're only beginning to uncover. Dark matter and invisible bridges. Dark matter is one of the universe's greatest mysteries. It neither emits nor absorbs light, making it invisible to telescopes. Yet, its gravitational fingerprint is everywhere. Galaxies rotate faster than visible matter alone can explain, implying that most of their mass is hidden. Estimates suggest that dark matter makes up 85% of all matter in the universe. But what is it? It's not made of protons, neutrons, or electrons, the building blocks of atoms. It could be composed of exotic particles like WIMPs, weakly interacting massive particles, or axions. But so far, experiments haven't confirmed their existence. Some scientists suggest dark matter might be connected to hidden dimensions or mirror universes, with particles that interact through forces completely unknown to us. These possibilities open the door to a reality far richer than what we see. If dark matter forms bridges between galaxies, holding structures together, then it might also serve as a gateway to new physics and perhaps even to new forms of matter and consciousness. Dark energy, the cosmic engine. While dark matter holds the universe together, dark energy is tearing it apart. In the late 1990s, astronomers made a shocking discovery. The expansion of the universe is accelerating. This defied all expectations. A mysterious force was pushing galaxies apart faster and faster. This force was named dark energy. Today, dark energy is thought to comprise roughly 70% of the total energy in the universe. But we don't know what it is. It could be a property of space itself, a kind of vacuum energy, or it might be a sign of physics far beyond our current theories. Some physicists speculate that dark energy might be linked to the multiverse, with our universe being just one bubble in a vast cosmic sea, each with different laws of physics. Others see it as a hint that space and time are emergent phenomena, not fundamental realities, but illusions arising from something deeper. Quantum foam in the subatomic landscape. Zoom in far enough beyond atoms, beyond protons and neutrons, and you enter the realm of quantum foam. At this scale, space-time is not smooth. It bubbles, fluctuates, and shimmers with uncertainty. Particles pop in and out of existence. Energy appears momentarily from nothing, governed by Heisenberg's uncertainty principle. This chaotic sea, known as the Planck scale, may be the foundation from which everything arises. Some theories suggest that even space and time are born from quantum fluctuations. If we can understand this layer, we may finally explain why the universe exists at all. Perhaps everything, galaxies, stars, consciousness emerges from this bubbling chaos. In that case, nothing is not truly nothing, but a fertile ocean of possibilities. Parallel universes and hidden dimensions. The idea of parallel universes may sound like science fiction, but in modern physics, it's taken very seriously. According to string theory, there may be 10 or 11 dimensions, most of them hidden from view. Our universe could be a three-dimensional brain floating in a higher dimensional space. If so, there may be other brains, each hosting its own universe, with different particles, forces, even laws of nature. These are the parallel universes of the multiverse hypothesis. There are many types of multiverse theories, quantum multiverses, where every quantum choice spawns a new reality. Inflationary multiverses, where each cosmic bubble has its own Big Bang. And holographic multiverses, where reality is encoded on a distant boundary. Could these universes interact? Could consciousness or gravity leak across dimensions? These questions drive some of the most speculative, yet tantalizing frontiers of modern science. Signs of intelligence at the edge. As we explore these hidden layers of the universe, a haunting question arises. Are we alone? Some scientists believe that advanced civilizations Type 2 or Type 3 on the Kardashev scale could exist on cosmic scales, manipulating stars, galaxies, or even spacetime itself. If such beings exist, their influence might not come in the form of radio signals or spacecraft, but in subtle anomalies in the structure of the universe, patterns, alignments, or phenomena that seem to defy natural explanations. Some have speculated that dark matter could be the residue of ancient megastructures. Others propose that the laws of physics themselves might be evidence of fine-tuning intentional design by cosmic intelligence. Though unproven, these ideas stretch our minds and force us to consider: what role does intelligence play in the fabric of reality? Wormholes, strings, and quantum tunnels. Einstein's equations suggest that wormholes, bridges through spacetime, are possible. Though unstable and hypothetical, these structures could connect distant parts of the universe, or even different universes entirely. In string theory, particles are not point-like, but vibrating strings whose harmonics determine the properties of matter. These strings might wrap around hidden dimensions, influencing gravity and other forces. Some physicists suggest that entanglement, the spooky connection between particles, may be linked to wormholes. This idea, known as R equals EPR, could mean that spacetime is built from networks of quantum information. In other words, the universe might be a vast network of quantum tunnels, a web of communication and connection stretching across all scales. Is reality a simulation? Perhaps the most provocative idea of all. What if we're living inside a simulation? Some physicists and philosophers argue that if it's possible to simulate universes with conscious beings inside, and if advanced civilizations can run many such simulations, then the odds are high that we ourselves are simulated. Supporters point to the mathematical nature of physics, the digital-like behavior of quantum mechanics, and the uncanny fine-tuning of constants in the universe. Even without evidence, the simulation hypothesis forces us to rethink reality. If we're simulated, then the true universe may lie outside our comprehension, but we might still glimpse hints of its architecture in the code of our cosmos. A universe still unfolding. We began this journey with the question: is there more to the universe than meets the eye? What we found is both humbling and exhilarating. Beneath the stars, beyond the atoms, behind the fabric of space and time lie mysteries that may take generations to understand. But each discovery, each anomaly, each strange signal from the edge brings us closer to the truth. We have not reached the end of science. We are standing at its threshold. We have unlocked a new layer of the universe. And there are many more yet to come. Let's keep looking up.